So I think I was at IBM when Tara came to IBM from MIT. She finished her PhD at MIT, and ever since she's worked for IBM. I remember when she came, people were saying, "Oh, Tara is our new superstar researcher," which I kind of objected to because I probably thought that I deserved that title.
Actually, I have to correct you. I came when you left, so maybe that's why they said that.
You were there. There was an overlap.
You left in like February. You came in June.
Really?
Yeah.
Okay,
So you still probably do have that title of superstar researcher there.
I had to admit at the end that it was probably true. So she's going to describe her latest and greatest.
Yes. Well, as much as they'll let me talk about, right? Okay, so before we begin, I want to acknowledge a lot of colleagues at IBM and also at the University of Toronto who have contributed a lot to this work. I guess everybody here knows what a DNN is. We can just skip this for now. We'll just go straight to the talk. So I'm going to just talk about 3 ideas that we've been exploring in terms of sort of improving word error rate and also speeding up training for neural networks. So I've tried to put a lot of stuff into this talk that I can talk about, so it's dense, but hopefully you can get an idea of everything that we're working on at IBM. So the first part is about extracting features from deep neural networks. So the most common way we've been using these DNNs recently is in a hybrid system, meaning we train them with a large number of output targets, take probabilities from the DNN, and we use them as output probabilities. We use them as the probabilities in the HMM. That's known as a hybrid system. Now, one of the problems with this is we know that we need a large number of output targets. Think of these as being the number of context-dependent states you have in your GMM system, on the order of 2,000 to 10,000. And what this does is it significantly increases the number of parameters you have in your network. So alternatively, if you train a bottleneck system or any sort of system to extract features from the neural network, they're generally trained with far fewer output targets. And then you can use your standard Gaussian processing techniques, speaker adaptation, discriminative training. So bottleneck systems is not a new thing. It's been looked at a lot in speech recognition. So when people were looking at shallow networks about 5 years ago or so, bottleneck systems actually performed better than hybrid systems because the hybrid systems were shallow, they were trained with few output targets, and the bottleneck systems were much better.
Just so we have a sense, what is few, what is many?
Okay, sure. So I would say many output targets is on the order of thousands. So like, somewhere between 1,000 to 10,000. On the order of few, I would say is like between 100 to 500.
Ignoring the previous works like on the tandem systems and that sort of things, you don't find it very useful?
I haven't done tandem. I think tandem would be useful on top of this. I haven't done any work in tandem, but yeah. There's no doubt tandem would add on to what I'm going to talk about even further. But I haven't done anything with tandem in this talk. So basically, when people started to look at deep networks, they found that if they used bottleneck features, this is a paper from Dong Yu a few years ago in InterSpeech, the bottleneck systems were actually worse than the hybrid DNN systems. And one of the reasons, I think, was because of the type of structure they were using. So I'm going to talk about a different type of structure we look at to extract these bottleneck features, which I'll show will allow the bottleneck DNNs to match the performance of the hybrid DNNs with far fewer parameters. So this was the structure that was typically looked at in the past. What they would do is they would train a neural network with a small bottleneck layer here in the middle. And then you train this to completion, and once you're done, what you do is you then extract out the bottleneck features here before the nonlinearity and use these as your new features for your GMM. So if we look at what these networks are capturing, we can see that the lower layers are doing some sort of speaker adaptation. The higher layers are doing some sort of discrimination. If you put this bottleneck layer here in the middle, the features can't capture all the benefits of this entire network, number one. And number two, you'll actually see that your frame accuracy will degrade here by putting this bottleneck here. And really, we want a set of features that's going to capture all the good properties about this network, the speaker adaptation, the discriminative training. So the idea is basically to first train a network.
Yeah, I think
I have another one. If you guys can't see it. Does this work? Oh, I didn't bring the battery though. I don't have the battery with me. No, I can't even see it. I don't have the battery actually with me, so we'll just have to not use a pointer. I can use the mouse or something like that if that's easier. Okay, thanks, Sanjeev. So the idea is that we're going to train a network with no bottleneck layer, a deep network with a small number of output targets here. And then what we're going to do is we're going to apply some sort of dimensionality reduction after we train the network. So this is right before the softmax. So one way to do this dimensionality reduction is to use an autoencoder, where you take the output before the softmax, and then you're effectively trying to reconstruct the input. So this is one way to do it. We've also looked at doing PCA or an LDA. They're all about the same in terms of performance. But the basic idea is that you first train the network and don't put any bottleneck in, so that your features that you're going to extract out afterwards will have all the good properties of the speaker adaptation discriminative training. Once you're done training this network, then you do the dimensionality reduction in however way you want to do it. So we tested this idea initially on just a small 50-hour English broadcast news task, and the DNNs, I'll get into the architecture of the DNNs on the next slide. But the first thing we wanted to explore was basically, do we actually need deep networks? Does deep networks matter in terms of giving good performance for the DNN features? So what we did is we trained two networks, a 4-layer network with 1,024 hidden units per layer, and a 6-layer network. We used FMLR features as the input to the DNN, and we cross-entropy trained these systems only. After we get the bottleneck features, then we go through with just with ML and discriminative training. So first of all, you can see that if you compare the hybrid and the DNN word RH, these are all cross-entropy trained systems for now. The DNN is much better, and you can see that deepness helps. So the better the original network, the better the features are. The second thing we looked at was, does pre-training actually matter? And so again, we compared two 6-layer networks, one which was pre-trained, one which wasn't. And you can see, again, we get an improvement in the on the hybrid side. We also get an improvement with the bottleneck features. And again, the bottleneck features are better than the hybrid system. So the trend seems to be the better you make the initial network, the better the bottleneck system features actually are. And at IBM, we do we do 3 rounds of training. First, we do pre-training, then we do cross-entropy training, then we do sequence training, because cross-entropy is a frame-level objective function, and speech is a sequence-level task. So we also explored, if we do sequence training, does this help the network as well? So you can see here, if you sequence train the network, again, we get improvements in the bottleneck features as well. The basic trend that we've seen is anytime you make the network better, the features that you get out are also better, and that makes sense. So the second thing another thing we explored is, what feature should we actually use to train this to train the network with the DNN? So you could imagine training using VTLN features to train the network. Then once you're done with that, you do ML training here. And then you could continue through with speaker adaptation, applying FMLR, for example. Or what you could do is train the network with FMLR features, and then, after that, apply discriminative training. So if we just compare this line here to this line, 21.8 to 21.5, that's about the same level of processing that's done on the features, though the order is slightly different. So what you can see is that if you train the network with FMLR and then extract the bottleneck features, this is much better than getting the bottleneck features and then doing FMLR on top. And I think intuitively the idea is, if you look at all the processing that we do to these features, at every stage the processing gets better. We never do discriminative training and then speaker adaptation, right? We always do speaker adaptation, then discriminative training. Because if you did it the other way, I think if you do speaker adaptation after discriminative training, you undo some of the benefits of the discriminative training. Again, these... I've tried that. Two FMLRs. No, you could probably, but I mean, this is trying to be the fairest comparison as possible, right? You can do that. You get a small improvement, but once you go through discriminative training, it's going to go away anyways.
No, I mean before and after the DNN features.
Yeah, you can, but I've tried it, but it's like 21.5 goes to like 21.3 or something like that. Once you do discriminative training, that doesn't matter. So we know that these. So basically, now that we compared, should we do? What happens if we actually do train our DNN with speaker-adapted and discriminatively trained features, so which would be, again, the same amount of processing as this. So you can see this is actually much worse. And the intuition, again, is that you have discriminatively trained features here, but these are sequenced, have sequence information in them. The bottleneck features are sort of frame discriminative. They're trained with cross entropy. So again, in some sense, if you apply a more powerful technique before, a sequence discriminative technique before a frame discriminative technique, then you're undoing some of the benefits. Yeah?
So we have a question here about why do we do all that? Because neural network is universal mapping.
Yeah.
So why does it matter what you do?
It doesn't. I'm going to get to this later. This is an excellent question. I'm going to get to this at the end of my talk. You don't need to even do any of this. Like, this is an excellent question. Yeah. Yeah.
So, I mean, this method sounds like what you're doing looks like an information bottleneck method. Why don't you just do that directly?
What do you mean information?
Information bottleneck.
What is an information
Well,
bottleneck?
you have three layers.
Uh-huh.
The one you train. You know, in some sense, you maximize the initial information in the first, you minimize the other, and then you have a trade-off between generalization and
information bottleneck takes into account the structure of the input. If the input is a vector.
Not necessarily. Why? Have the outputs already.
Also, the continuous variable.
That may be the trouble, but
I don't understand the question. There are bottleneck methods going back for decades, and
information bottleneck.
Yeah, Tishby proposed specifically.
Yeah, that basically.
I know. Tishby proposed specifically information bottleneck for something that didn't look at any metric structure on the input space. It's only taking advantage. It's only looking at mutual information between input and output.
But then you're really also maximizing input in the middle layer, maximizing middle layer power. The other way around, minimizing middle layer power. That's really what you're doing essentially. And the beta, the parameter that the trade-off parameter that you treat.
I know how it works, but it also throws away information that Tara wants to use.
Okay, let's get back to
Anyway.
So I think the takeaway message from this is whenever we do feature processing, we always want to, at every stage, we want to have a more powerful representation than the previous, right? So bottleneck features are basically doing some sort of frame level discrimination. So we want to do that before we do the sequence discriminative training with the GMM. So then what we did is so we now know we want deep feature, deep networks, what type of input feature we should use. So we took this recipe that we learned on the previous slides and we applied them to 3 large vocabulary tasks. So broadcast news and switchboard. So all the DNNs here are trained with FMLR features. I've cross-entropy and sequence trained these systems. And then once we get the bottleneck features, we go through with ML and then discriminative training. So what you can see is, first, the hybrid or the DNN features offer a big improvement over the GMM, 8 to 15% relative. This is standard with gains that we're seeing in the literature across tasks. But more importantly, what you can see is that the hybrid DNN and the DNN features have a very similar word error rate. Sometimes, you might find the DNN features is 0.1 or 2 worse than the hybrid, or 0.12 better, but they're all about the same. So we can achieve sort of the same performance as the hybrid DNN with far fewer parameters, because we just by using a network with 512 output targets rather than the switchboard system, for example, which is 9300, that results in a 50% reduction in the number of parameters, or a 2 times speed up.
And when you say number of parameters, you think about the parameters in the
I'm talking about the number of parameters in the network, not the GNM.
Yeah, because I'm thinking that the back end, if you will, is simpler. Whereas with the DNN features, you probably have distributive training and so on and so forth.
Yeah.
So you probably have a bigger system on the back end as well, right?
Yeah.
So you don't mean that it's bigger even after you count everything?
No, no, I mean like just the number of parameters of the DNN only, not everything else that went into that. Yeah. But so another nice benefit of DNNs is, so when we train these DNN features is when we train hybrid systems, we do cross entropy and sequence training. That sequence training gives us a huge win in word error rate. So to give you an idea, this is the word error rates on 400-hour broadcast news and 300-hour switchboard of a hybrid system cross entropy and sequence trained. You can see we get about 10% relative improvement just by doing sequence training. But let's say you don't want to do sequence training. Sequence training is can be difficult to implement. It's slow. So alternatively, what you could do is you could just take a DNN train with cross entropy, dump features there, and go through with GMM discriminative training. You can see you still get a very nice improvement over a DNN hybrid system. It's not as good as the DNN hybrid with sequence training, but it's not that far off. And if you do want to go ahead and do sequence training with the DNN-based features, you can it will come very close to the performance of the DNN hybrid system. And another nice benefit of DNN feature-based systems we've seen is, let's say we want to train systems on 10,000 hours. We've seen we can just train these networks with 300 hours, dump features. All you're learning is a transformation. Apply that transformation to 10,000 hours and build Gaussians there. That's a lot faster. So there's a lot of very powerful benefits with these with DNN features.
How small have you gone on your DNN?
How small in terms of hours or a number of hours?
Train on, let's say, just
Oh, I've trained Timit, which is like 10 hours.
no, meaning the last fact you mentioned, namely you train your network on 300 hours, then just process 10,000 acoustic training speeds and build a system.
Yeah. I haven't gone lower than 300.
I see.
Yeah, so I don't know. It's a very good question. I don't know.
Well, then ceiling is another man's fault.
No, I'm just saying, maybe with 10 hours you get good enough features that you don't need anything else.
I don't know. It's definitely something worth investigating, right? Because who wants to train systems on 10,000 hours if you can just get the transformation as well? 512. And we experimented. I didn't show it in the slides, but we experimented with the number of output targets, and we found about 512 is better.
I was not entirely clear how you get features out. Can you just summarize that?
Okay, so you train the network, and then before you take the layer before the softmax, before the nonlinearity, and then you apply some sort of dimensionality reduction there.
So can you go back to that picture? You had these two stacks.
That's exactly the tandem.
No, but then tandem applies after that. You take the initial feature and then you apply both, right?
I think that's a common misconception. It turns out that in Enak's original paper.
Okay.
That's fine. I fight for it a little bit. I normally don't do it, but there's one thing which I kind of know.
Okay.
Huge universe which I don't know.
Okay, no, thank you, Hina, for correcting it. So we'll be more careful about that in the future. I had thought more recently that tandem was when you take the output and then you concatenate the original input to the network, and you do a PCA on both, which will give you even better improvements. But we don't do that. But I think, yeah.
Just real quick, question.
Uh-huh.
So you say you train with DNN.
Yeah.
Like that's like 3 hours, right? So
Yeah.
like is there any improvement from going deep relative to just the standard thing that we can
Yeah. If you look at some of the work out of Jeff Hinton's group, we'll actually have plots that shows you the reduction in word error rate per layer. I don't remember numbers off the top of my head, but I want to say at least you get a 3% improvement by going from 2 layers to 4 or 5 layers. Yeah. They're down to 17.7 on Timid now, which is Jeff Hinton's paper in ICAST, which is very impressive. Okay, so let's say you don't want to use bottleneck features. You still want to train a hybrid system. So again, as I was saying before, one of the problems with these hybrid systems is we have a large number of output targets, and that makes the training very, very slow. So to give you an idea, for example, let's just take switchboard, which is about 100 million training examples, 300 hours. So the DNN is about 43 million parameters. It's 2,048 hidden units per layer, 6 layers, and 9,300 output targets. That takes us roughly 2 weeks to train with everything, pre-training, cross-entropy, training on the GPU, and sequence training, which is parallelized. Now, compare this to a GMM, which is just 16 million parameters and takes 2 days to train. Now, most of the parameters in this DNN are basically due to this 9,300 output targets. Like 50% of the parameters just sit in this last layer. So the idea is basically, we know that in the output layer, the following 2 facts are probably true. Very few classes are probably active, and most of the classes that are active probably belong to the same context-dependent state. They're correlated. So if that's true, we thought maybe we can represent this last layer in the network as one with low rank.
Okay, so that means you have, in a given context-dependent state, you have multiple classes, like mixtures.
No, because we're going to take the layer before. It's not the last layer, it's the one before that. It's basically this.
But they're not classes, though. They're just...
Maybe I can show you visually on the next slide. Maybe that'll make it more clear. So the idea is if you're given any matrix C of rank R by the rank factorization algorithm, you can express C as A times B, or A is M by R, and B is R by N. So the idea is like, what should R be so that you can appropriately represent the matrix C with one of low rank? So visually, what we mean is this. Maybe this will make it more clear. So we have our network here, where each layer is going to be a linear weight multiplication and then a nonlinearity. And let's take look at the last layer here. So the last layer is 1,024 by 2,220. We're going to take this, and this is what we're going to say will represent as 1,024 by R, and then R by 2,220. So we haven't changed the number of context-dependent states here. And then we put this through the softmax. So if we choose R to be small enough, we can greatly reduce the number of parameters. So this is a simple experiment we did on broadcast news, where we looked at the word error rate for different choices of this rank value R. So the baseline system is at a word error rate of 17.7 with 6.8 million parameters. What we found is we can reduce the rank all the way to 128 with no loss in the word error rate and roughly a 28% reduction in the number of parameters. So if we take a little bit closer look at why 128, this graph right here is showing a histogram of sort of the number of active targets for across a variety of utterances. You can see the number of active targets. When we're saying it's active if the activation is above a certain threshold, but it's very low, I think like 0.1e to the minus 3 or something. And you can see that roughly 100, a little bit more than 100 something is what's active. So this seems like an appropriate choice for this task. And I'll get into how this rank is tuned on other tasks in a few slides.
So the active targets are the low.
Yeah, are the outputs after the softmax. Yeah, the classes you want to.
So is this just equivalent to another layer with no knowledge?
Yeah, that's exactly right. That's exactly it. So then we thought, can you do this low rank on other layers as well? So we looked at applying the same factorization to the penultimate layer. So what we find here is that, so the baseline now is the 17.7. This is 5 million parameters. So this is the low rank applied to the final layer only. So what we find is that if we apply the low rank to that second to next layer, even for different choices of the rank, we don't get, this is not 32 million. This should be probably, I think I've switched this. But basically, we don't get any reduction in the word error rate, and we get a very small reduction in the number of parameters as well. So it seems that, applying, it's really only the softmax layer that seems to have that low rank property. The other layers in the network don't have that property. So we also looked at applying low rank to sequence training to see if we would get any benefit in terms of training time on that level as well. So again, we use the same rank 128 that we use for the cross-entropy training. and what we find here is a full rank system has a word area of 14.7. We run this for roughly 24 iterations, and training time is 18.7 hours. And this was computed on, I think, 12 machines that were poisoned. So this training, so no other machines, no other jobs came onto the machine at this time. So we know already that the rank, we can reduce the number of parameters of the network by 28% with the low rank. But what we also find is that
12 machines, this is for cross-entropy or sequence?
this is sequence training. Yeah, so this is parallelized. So what we actually find is that with the rank of 128, again, we don't take any hit in the word area, which is nice. The number of iterations is significantly reduced now, reflected in a much smaller training time. So this is roughly a 55% increase in the improvement in the training time, just for a 28% reduction in the number of parameters. And some of the theories we have is that when you use a slow rank, you're sort of constraining the space of search directions. That might make Hessian for you more effective.
Just sort of curiosity, I think it's triggered by Dan's remark. Did you look at just reducing the size of that layer, maybe to 128%?
The last layer?
The penultimate one. Because after all, if you do this rank reduction, what you're doing is you're taking your 1024 outputs, mapping them to 128, and then mapping them back out to 20.
But that would put a bottleneck in the system, basically, which I know will degrade the frame accuracy.
Yeah, but you already have a bottleneck.
But you effectively have it, right? Because you're reducing that.
But are you saying put a bottleneck with the nonlinearity? So you're like 128 here, where this is like the weight plus the nonlinearity, and now you have 128 down to 2,220.
If the network wanted, it could just use a small range with it, so it doesn't have to use the nonlinearity. That probably wouldn't happen.
I mean, are you saying put a nonlinearity, like you have a weight plus nonlinearity going into 128, and then you have, but that would be a bottleneck. I mean, that would actually be, but I don't have any nonlinearity going into there, and I think.
Yeah, so you could control for that. I mean,
in what sense? Like you could control. What do you mean you could control for the nonlinearity?
Nonlinearity is another parameter that you tune, don't you?
Not really. I mean, you're right in the sense of you could control the alpha on the nonlinearity so that you don't have it to be as sharp. Yes, that's something you could do.
What I'm trying to figure out is whether this rank reduction is something fundamentally different, whether it's just the network being constrained to reduce parameters.
Well, the idea was that it's a network constraint to reduce parameters, but the idea was that if this matrix actually has low rank, then we know we can represent it by two smaller matrices. Where, right? If this matrix C actually has low rank, I can actually represent it by A times B.
No, what I'm saying is that regardless of whether it has low rank or not, you're choosing to represent it that.
Yeah.
So that's basically saying it's a little bit like saying I'll have a layer in between with no nonlinearity, which is bottleneck.
Right, but so the bottleneck that I think we were talking about before, so if you do something like this.
In other words, I wouldn't bother calling it rank reduction, I'd just call it between the next parameter.
Yeah, but if you do something like 128, let's say you have like weight and then nonlinearity here, and this goes to 128, and then you have something which is like weight and the softmax going up to whatever it is, 2200. Okay, you will see that you will degrade the frame accuracy by doing this because of this nonlinearity.
Yes,
right. So if you, that's effectively what we did, right?
Yes, I'm saying why do you call it rank reduction rather than saying we have a particular network architecture?
Because the idea was okay, terminology-wise. I mean, yeah, sure. We can change the title. Anyways. So then what we did is we saw how robust this was for larger tasks. So I explored this on 400-hour broadcast news and 300-hour switchboard, where the number of output targets is even larger. So in 400-hour broadcast news, it's roughly 6,000 output targets. So you can see that with a rank of 128, we get a 50% reduction in the number of parameters with no loss in accuracy. And for switchboard as well, it's roughly a here, the rank I choose a little bit larger. This is 9,300 output targets, and I get a 32% reduction in the number of parameters. Now, you see that the word arrays here are slightly higher, but after cross-entropy training, this difference, after sequence training, this difference goes away anyways. And one of my colleagues, Ebru Arsoy, actually looked at this technique for language modeling as well. You can't ask me too many questions about all this because I'm not really a language modeling person per se, but the DNN here was trained with 10,000 output targets, and what she found was, I believe this was Wall Street Journal, and she also found this is the baseline system, 20.8, and 8.2 million parameters, and she found that with the rank of 256, she could get roughly a 29% reduction in number of parameters, and for a little bit larger loss in the word error rate, 21.0, but it doesn't matter. Once you do your scoring, you get effectively the same word error rate. You can get almost a 50% reduction, or 45% reduction in parameters. Okay, so now the third topic is on convolutional neural networks. So we know DNNs are low. That was on low rank. It was on deep neural network features. Yeah.
DNN, not convolutional.
Yeah. I'm just trying to give you guys an idea of like sort of everything that we're working on. So, yeah. Okay, so this is on convolutional neural networks. So we know DNNs are very powerful, but one thing they don't really model well is one notion is this was translational variance. So it's very obvious that removing any variance in the input signal is going to improve classification performance. We've been doing this for years with speaker adaptation and noise robustness techniques. But DNNs aren't designed to explicitly model this translational variance as opposed to CNNs, which I'll get into in the next few slides. So CNNs are nice because now you can sort of model this translational variance with DNNs if you have large enough networks and lots of data. One of the nice things about CNNs is you can model this translational variance with far, far fewer parameters than the DNN. And I'll get into what this means on the next few slides. Secondly, the DNNs ignore the input topology of the signal. So the input, as long as it's in any fixed order, will not affect the word error rate. But spectral representations of speech have very, very strong correlations, and it would be very good to model this. And CNNs, in fact, do model these correlations. So these are the two motivations that we were looking at when we explored CNNs. So as I said before, it's very obvious that we want an input representation which is invariant to speaker characteristics, noise characteristics, whatnot. And we've been doing this for years in speech. So you could just train a DNN with these speaker-adapted, noise robust features. But one of the reasons that I'll show on a few slides is the CNNs are a little bit more powerful than that, because what you're doing is you're sort of reducing the spectral variation, and you're modeling the correlation in the input signal jointly with actually doing the classification. That's very different than the DNN, where you're already given the features ahead of time. And I think it's this joint aspect of it that makes the CNNs very, very powerful. And some motivation from the vision world is CNNs have shown far better performance than DNNs in vision. This is a lot of work out of Jan LeCun's group. So before I go through and explain more conceptually what is a CNN, let me just go through the DNN weight multiplication. That way you can compare it to a CNN. So we first take our weight matrix W across some frequency and time patch, and our input signal X, and we're going to multiply the two together to get a set of hidden outputs. And then we're going to just slide this filter across time. But notice the filter spans through all of frequency. Between 9 and 11 frames. Yeah. So now let's look at a CNN. So again, we have our weight matrix, and we're going to multiply our input signal X. But now the weight matrix is going to span a much smaller frequency patch. We multiply the two together to get a set of hidden units. set of activations. And then what we do is we take the filter and we slide it across frequency. And we get another set of feature maps. This extends on to 4, though I haven't shown it here. And we keep sliding this across frequency. Yeah?
I don't understand how your previous slide is actually saying what a DNN does. Because it seems like you have the same parameters for each. Suppose you have a window with 3 frames.
Uh-huh.
It seems like you have the same parameters for each one. And also, I don't understand the. Is it like each?
Think of it like a set of those as like a mini batch, basically. And you're applying the same weight to that mini batch.
So each one sees just one.
Yeah, you could think of it as you can think of that long slice as a mini batch, basically. Okay, so basically what we have is we have a set of activations and across feature maps now. So this is just a convolutional multiplication. So a full convolutional layer actually consists of 2 things. It consists of doing this using these locally connected filters, and then using a concept called pooling, which removes the variation. So if we look visually, each of these weights here is going to is each of the weight of the same color, or each of the line of the same color is the same weight that's shared across frequency. Here's the input, and here's the activations that result from the multiplication. I'll get into that. We've tuned all that. Yeah, I'll get into all of that. In this slide, it's 3. So what we do is then we say, most probably all the hidden units belonging to different feature maps, most probably are predicting. They're going to be predicting the same sort of feature, but each of those might be slightly shifted up or down due to speaker characteristics or whatnot. What we want to do is we want to remove that invariance. So we're going to do some sort of averaging or pooling. Pooling can be done by taking the max across this window, or the average, or the LP norm. We've tried all of them. They're all about the same. But the basic idea is to do some sort of averaging to create more invariant features. So visually what this looks like is, well, we only pool in frequency. I know Jan pools in time. I haven't found that to be effective in speech, but that's still a very open problem. So there's, right now for this work I just pool in frequency. And so basically what this visually looks like is that you're just going to reduce the frequency dimension and keep the same time dimension. Yeah. But effectively why I don't pool in time is if you pool in time without overlapping the pooling windows, you're effectively subsampling your signal by some factor, by your pooling factor.
Can we imagine it as a big block that's being shifted a little bit, or a little block that's being shifted a lot? The actual.
What do you mean a big block that's shifted?
Well, like, you have these pictures of blocks. I just don't know whether you're shifting by a little bit in frequency, if you're thinking that each one can see a lot of frequencies, or whether each one can see a small amount of frequency, but you're shifting them all the way up.
Oh, so the pooling is very small. It's only done over like a small frequency range, like 3. Yeah.
So you have 40 meltfilter patches, right?
Yeah.
What's the size of your patch?
So it's 9 by 9.
Oh, 9 by 9.
Yeah. This is all tuned, but usually for the first layer we do 9 by 9. There was a lot of experiments that went into. So basically the idea is what's the correct CNN architecture. So all I've described to you now, up till now, is what does a convolutional layer do. It does this local multiplication and then pooling. So the idea is how many convolutional layers do we want? How many fully connected layers do we want? So you can think of the convolutional layers. We've visually actually seen this. I haven't shown the plots, but I've visually seen. Basically, the convolutional layers are doing some sort of speaker adaptation. They're extracting invariant features, and the fully connected layers are doing the discrimination. So we did an experiment on broadcast news. This is all, the input features here are all log Mel filter bank coefficients. And so you can see that the optimal number of convolutional layers is roughly 2 and 4 fully connected layers. And you can also see that for the same input feature, the CNN is much better than the DNN.
It's 9 by 9, so it's like 9 represents 90 milliseconds, and 9 in frequency represents about 3 bar or
Yeah.
And
Yeah. So the 9 by 9 is what's used in this first layer. In the second layer, it's 3 by 4. Yeah. So I've tried 4 by 15 and 15 by 4, and I've tried all sorts of combinations, but that's what seems most optimal. Okay, so there was actually a paper by Abdel Rahman last year on CNNs applied to timid. And basically what he does is he does this notion of limited weight sharing. So he splits this. So the most simplest way you could think about this is, let's split the spectrum around 4,000 hertz. That's roughly where the fricatives start and the vowels end. And let's just have a CNN that's trained just on the low frequency part and one on the high frequency part. So it just learns to do discrimination in the region that's really the most confusable. So this is ideas known as limited weight sharing. And so one of the problems with this is, in some sense, you have to make a hard decision ahead of time on where you want one limited weight to start and to end and another to begin, even though you can have some overlap. And in his paper, it was a little bit harder to add in these extra convolutional layers. So we thought, well, let's just use full weight sharing, but have more hidden units to explain the high frequency and low frequency variation. So we have a full weight sharing that shares across all frequency, but we use more number of hidden units. So the benefit of this is that we don't have to make any hard decisions about where filters start and end, and we can easily add extra convolutional layers. And this is really what's done in the vision community, not the limited weight sharing. So what you can see is if you increase the number of hidden units, you get good improvement in the word error rate. I didn't go above 108, 256, because then I wanted to make sure for all these experiments my number of parameters match the DNN. I have done experiments since then where I've gone even up to 512, and I do continue to get improvements in the word error rate. But I tried to keep these experiments as fair as possible to the DNN for now. And I've also compared this to limited weight sharing. It's just for the convolutional layers. Yeah, 128 is the number of hidden units for the first convolutional layer, and 256 is the number for the second convolutional layer. Yeah. And so so I've also compared this to limited weight sharing, and the behavior is about the same. But this is a lot simpler to implement because you don't have to make these hard decisions and you don't have to have in your code, different weights and whatnot. So we prefer to go with this approach. Okay, we also looked at what type of pooling strategy, how should we pool, what should be the size of the pooling window. So we have the way pooling works is you have a time frequency patch that you want to pool over, and the most common approach is just to pick the max of this, so let's say 2.4. So we compared pooling for both switchboard and broadcast news. And the reason we wanted to compare both is broadcast news is 16 kilohertz and switchboard is 8 kilohertz. So we wanted to see if there was any difference in the pooling between the two. This is pooling on the first layer only. So you can see that a pooling of 3 helps is the best for both cases. And in the second layer, I found that you don't need to pool at all. Pooling will hurt you in the second layer. Yeah, I've tried all this, but basically you can think that your MEL filter bank gets larger in the higher frequencies, so in some sense each band is capturing the same sort of information, so you don't really need to pool more on the higher frequencies. I've actually tried it, it doesn't help. And that was my intuition, because you already have an equal amount of information in each band anyways. Okay, so we also explored what's the best feature set here. And as I said before, we need the features to be locally correlated in time and frequency for CNN, so that means no LDA. So one of the features which satisfies this is MEL filter bank coefficients. So what we did is we looked at various transformations of these features to find the best feature set. So first we see that doing VTLN warping gives us a small improvement. Now with FMLLR, we actually didn't find much improvement at all. I think one of the problems is FMLLR assumes diagonal covariance, and so you don't want your features to be correlated. And the features are correlated here, so maybe doing something like an STC on the FMLR and then doing FMLR and then inverse STC might help. So I would take this number with a grain of salt because FMLR wasn't really done correctly here. And again, we see using delta plus double delta helps, but then the energy doesn't help a lot. So these are really the best features that we're using right now for the tasks I'll talk about. No, so each of them becomes like a different feature map as input into your network, yeah. Yeah.
So there's no backend. This is it, CNNs, and that is the result. I mean,
You have 2 convolutional layers and then 4 fully connected layers, but there is no fancy processing to these features at all. Well, I'll show you, right? What happens at the end now? That's the. Okay, so these are initial experiments we did on 50-hour broadcast news. So the DNNs here are trained with all the fancy feature processing, FMLR. Okay, those are the features that give us the best results in DNN, and we've cross entropy and sequence trained them. And then we compare this to a CNN, which is just trained with log-mel filter bank, coefficients VTL unwarped, and the delta plus double delta. I compare this in both the hybrid setup and a DNN feature-based setup as well. So what you can see is that both for the hybrid CNN or the feature-based CNN, we get between a 3 and 6% relative improvement over the DNNs. Whether it's hybrid or feature-based, it doesn't matter. Mm-hmm. Yeah, are you sure? This is like but how much data is he using to train the network? So I think you guys are using the 400-hour broadcast news setup. This is 50 hours. Because this is the best 50-hour number we have on this task. So most probably you guys are using 400 hours. Because the 400-hour number, I think, is closer to 15. Sorry, the GMM number here is like closer to 15, I believe. And also this, I mean, if you want to get the details, this DB is actually manually segmented, but I think the one you guys are using is auto-segmented as well. Yeah, so again, don't compare this Devo4 number to the previous one because the DBs are slightly different. Just compare the trend in the slide. So then we looked at this on 2 larger tasks, broadcast news and switchboard. Again, DNNs are FMLR trained, and the CNNs is just log-mel filter banks. And we apply the standard pre-training, cross-entropy, and sequence training. And again, you can see on broadcast news we get a 10 to 12% relative reduction in word error rate, and on switchboard 4 to 7, depending on the test set. Okay, so let me just conclude the talk with the 3 areas that I talked about. So first, talked about DNN features, which we found to offer between 8 to 15% relative improvement over GMMs across many different tasks. But the benefit over hybrid DNN is that it allows for a 2 times speed up in training because of the reduction in parameters. And again, if sequence training is challenging, this gives this type of idea gives a significant improvement over hybrid DNNs, which are just cross-entropy trained. We then talked about low-rank factorization, which gave a 30 to 50% reduction in number of parameters. And this has been observed across a variety of acoustic and language modeling tasks. And then I talked about CNNs, which are more powerful than DNNs because they model the spectral correlations and reduce the spectral variance jointly while doing the classification. And here we see they give between a 4 to 12% relative reduction over DNNs. And these are the 3 different papers from ICASP that that discuss in more detail the work I presented. Thank you very much. I'll take any questions.
Also good time.
So the idea of using original networks, which were not meant to really deal with signals that change over time, it's kind of very surprising that you get good results. I guess you get some indication why, if you look at correlations, and still, we've been doing that for acoustic sound classification, and we've been pretty that this really should never work. We're getting pretty good results,
Well, convolutional neural networks wouldn't work in time if you pool.
I know, but that is, I know all the, right, actually
No,
we have.
but Andrea, she is not doing any convolution on the temporal axis.
Yeah.
If I understand
Well, but she's
correctly,
really
she's doing the convolution only on the
frequency.
frequency axis.
Right, but she does also a little bit of pulling. The first slide you said,
I pool in frequency only, I don't pool in
the
time.
first example you showed was pulling in time.
It's pooling in frequency.
No.
Or
Only
in the little diagram that you showed.
It's pooling in frequency.
Well, then it's understood, yeah.
So you tried pulling in time and it didn't work, right?
Okay, if you pool in time without any overlapping window, you're subsampling your signal by 2. If you pool with an overlapping window, I think that should help.
Yes, we don't, yeah.
But I haven't tried that.
Okay. No, it's
This
okay.
is all in.
So I was looking at the first slide that you showed. Go back. That's why I was confused. Go back. Right there. Isn't that time?
But this is a DNN, and you can basically.
Oh, this is DNN, sorry.
Yeah.
Okay.
And you can imagine that you're just shifting
No,
your.
I thought it was, that's what you
No.
mean. Okay, I didn't read CNN.
Yeah.
Okay.
Okay. So let's. I don't like these things to go on too long. It gets exhausting. So and I know Tara's woke up super early this morning. So let's thank the speaker again.